Thank you very much. I'd like to thank my co-authors, Scott Bortson and Changfei Dong. Well, the objectives today we want to talk about is how the magnetosphere affects outflow. And of course, we see and have heard many times that magnetospheres do indeed focus loss processes from the cusp, the polar cap, and the auroral zone. So what we want to tease out is what happens when both the exoplanet and its exomoon have magnetospheres. Well, if we look at our example, the Earth, our moon has made the Earth what I would call, and many have, uncommonly habitable, provides tides, provides stability in climate, also stabilizes our obliquity. And so would an early moon or exomoon magnetosphere also protect that exoplanet? That we think we also can make some comments on. Now we're going to take the Fran Bagenau approach, which is keep it simple. And we'll start the process by using what we've learned about the Earth-Moon findings. Now, what's happened over the last couple of years is some really great things looking at Apollo samples that have told us that the early moon did indeed have a magnetosphere for perhaps as long as 500 million years. We're going to use the current lunar origin model, of course, the giant impact hypothesis, for which a large, perhaps Mars-sized object hitting the proto-Earth, creating then the moon as it reaccretes outside the Roche limit, okay? And then over time, tidal forces move the moon away from the Earth, and therefore the exomoon away from the exoplanet. Now, to model this, we're going to use absolute simple stuff. We're going to use a magnetic topology that is a simple dipole for both the exoplanet and the exomoon. So here are the magnetic topology results for the dipoles of the exomoon and the exoplanet anti-aligned. We've also done the aligned example, but I don't have time to talk much about that. What we have in the top panel and the bottom panel shows us these noon-midnight meridian cuts of the magnetic field topology at several locations of the exomoon at 4 planetary radii, 8 planetary radii, and 18 planetary radii. We show in the top 3 panels when the exomoon is on the night side at midnight, and the bottom 3 is when the exomoon is on the day side or at noon. And what we see, of course, is the magnetic field of the exoplanet is encompassing the exomoon in all these examples. And therefore, the field lines on the of the exomoon are always closed. There's no open field lines on the exomoon in these examples, both when the moon is on the day and on the night side, of course. Now, the time representation is done by distance as the moon moves gradually away from the exoplanet. Now, what we see on the top panel is indeed the exomoon field lines crowd up, in particular at the higher latitudes. This moves those field lines into the polar cap region, where it's typically open field lines, but then creates closed field lines. The bottom 3 panels show us where the exomoon on the day side really provides a great barrier against intense solar wind. As you see, you have another magnetosphere in the way. In fact, the exomoon magnetosphere has a tendency to push the cusp to higher latitudes, and therefore moves it also further into the polar cap, reducing the size of the polar cap. Relative to the closed field lines, in this particular example, we can look at data from the IMAGE satellite. The EUV instrument has seen and observed the plasmasphere, and indeed those closed field lines capture the ionospheric outflow. In this simple cartoon, it creates the plasmasphere. The plasmasphere stops filling when it becomes, when it gets into equilibrium. Diffusive equilibrium occurs, the filling stops. We see that at Earth. And so the closed field lines aren't going to contribute unless they're radically reshaped by intense solar wind over periodic times. And of course, now as we also introduce the Exomoons magnetosphere, that provides a whole set of other closed field lines for which the filling would begin. There may be enough time to fill those field lines over a several day period. That, of course, depends upon how far the moon has evolved away from the exoplanet. If we take a different view of this whole process and we look down on the YZ plane, in other words, the orbit plane, and we concentrate on the field lines from the exomoon that connect to the high latitudes of the exoplanet, we see in the top three panels at the same distances where those field lines extend over a number of longitudes, and therefore that inflates the magnetosphere of the exoplanet. This is also the case, as you see on the bottom example, where we have the exomoon on the day side, and the exomoon actually has this major barrier against intense solar wind as it occurs. And once again, it inflates the exoplanet's magnetosphere. And that, of course, depends upon the strength of the magnetic field. We now also then can look at those field lines in particular and map them onto these polar grids. When we look at the exomoon at noon, we see then all these field lines in the polar cap of the moon, exomoon, does indeed connect and close on the field lines of the exoplanet. We see the exoplanet field lines then that are open inside the oval area begin to reconnect or connect to the exomoon field lines. A Mercator projection of that is shown at the top, illustrating the distances. And so as the exomoon moves away from the exoplanet, we see then those field lines that are connected, therefore closed and not open, interacting into the open field line areas. And so the maximum amount of area that these field lines take away from the open field lines is about 20% when the exomoon is on the day side. In a similar plot, when we look at the exomoon on the night side, once again, all those field lines in the polar cap region of the exomoon do indeed connect to the exoplanet, begin to impinge upon the polar cap or the open field line areas. And it's, once again, the maximum area is indeed about the same. It's about 23 degrees. And of course, we haven't observed exomoons. We're in the process, I think, of an exciting era of looking for exomoons in the data and developing techniques and capabilities to look for exomoons. And one of the top techniques that's being talked about, of course, is to leverage the concept that these, like the Earth and Jupiter and other planets with magnetic fields, generate radio emissions over the precipitating auroral zone. These are escaping electromagnetic emissions, typically in the tens of kilohertz to megahertz range. And of course, if it's a Jupiter-like system where we have the moon interacting with the planet itself, then we might see these cones or filled in open, hollow cone or a filled in cone moving around indeed with the exoplanet. That would be wonderful. It would give us all kinds of information about the field strengths and about the exomoon itself. Like at Earth, without a radiation coming from a magnetosphere from an exomoon, we have auroral kilometric radiation, and of course, that's very characteristic of the field lines that we see. The key is that we are quite interested in getting a lunar far side array, and a lot of discussions going on in this area that might have the ability and sensitivity to begin to see these radio emissions associated with magnetospheres. So in conclusion, we've modeled exomoon, exoplanet magnetosphere topologies. We're using a very simple dipole magnetic field capability in this analysis. And of course, we're using what we know about our own Earth moon creation story, and that is the giant impact hypothesis. It's clear that the resulting coupled magnetospheres work together to protect the early atmospheres of both the exoplanet and perhaps even the exomoon as it begins to outgas. It also will go through those processes of ionization and outflow, but will be on closed field lines, retaining some aspect of that atmosphere for a longer period of time than when it would normally have occurred without a magnetosphere, of course. Now, this may be critically important during times of the early evolution of these planets because of the early evolution of the young stars that they're associated with it, and in particular when the habitable zones are close to the host stars. Now, as the exomoon distance from the exoplanet increases, the extent of the exoplanet open field lines also begins to decrease to about 23%, as shown in this simple analysis. So let me end by just saying in the evolution of exoplanet atmospheres, in particular for creating a habitable environment, another factor that we may be wanting to look at is whether the exoplanets have an associated moon with strong magnetospheres. Thank you very much.
All right, thanks very much. Very interesting talk. We have a couple of questions on the chat. So the first is from Arnav Basak. Do you expect exchange of atmospheric species between the two bodies due to the reconnections? And should that depend on stellar wind magnetic field orientation as well? And then what about the case of aligned dipoles?
So I'll start with the last one. The case of the aligned dipoles has a little bit different story because the magnetosphere of the exoplanet must surround now a larger bubble. It pushes those field lines, and instead of having connected field lines, it takes its own field lines and begins to encroach, making the polar cap smaller. So that's an effect. Didn't have an opportunity to show that due to the limited time. The first part of the question is indeed, we're now looking at the Earth-Moon example where we want to go into these permanently shadowed areas. We want to core what we believe is a significant amount of volatiles that are in there and begin to spread them out and look at it and look for potential signs of early Earth atmosphere. We already know that there's nitrogen embedded in the moon. That's been a mystery for quite some time. The concept that it had a magnetosphere may have enabled the Earth ions like nitrogen and oxygen to be impinged into the solar surface. So we're pretty sure that the nitrogen comes from Earth, but we don't understand exactly that process. But the magnetosphere coupling example that I showed may indeed be that. And that's why looking at that history and the stratigraphy in the permanently shadowed areas might really give us that insight as to what's going on.
All right, there's a few more questions. So would it be easy to distinguish between possible radio emissions from the exomoon motion in the exoplanet magnetosphere or the exoplanet motion in the stellar magnetosphere?
The radio emissions that we're talking about are generated by Doppler shifted gyro emission, and therefore they give us a hint as to the strength of the magnetic fields. It also, we want to look for whether these cones are hollow or filled. If the cones are filled, like they are here at Earth, even though the radiation is generated perpendicular to the magnetic field, we know that the source regions are deeper into the ionosphere, and therefore there's a lot of reflection going on. If they are like Jupiter, where the cones are generated at a higher altitude relative to the density of the ionosphere itself, they retain their openness, they retain their hollowness. And then, of course, as the moon, which is in control of that emission, moves around the planet, that will also tell us the distance of the exomoon from the exoplanet. So there are just a couple characteristics from these radio emissions that we can get